Hello, and thank you for clicking on the video PowerPoints for Chapter 7 in your Modern Welding textbook. Chapter 7 is Gas Metal Arc Welding and Flux Core Arc Welding Equipment and Supplies. There's a lot of information in this chapter, so we're going to try to take it one slide at a time. We'll also be flipping back and forth from the textbook, so hopefully you can follow along. This can answer any questions that you may have after reading the chapter, and it's a good way to supplement your learning. So let's get started. Chapter 7, Gas Metal Arc Welding and Flux Core Arc Welding Equipment and Supplies. I will refer to this acronym GMAW as MIG and this acronym FCAW as Flux. Just a little easier and a little less work for me. Learning objectives: describe the function of MIG and flux station components. Identify the various types of shielding gases used in MIG and flux. Describe their characteristics and evaluate their effectiveness. Identify and specify the various electrode wires used for MIG and flux using the tables provided in the book as AWS Electrode Classification System. Arc welding. Gas metal arc welding, or MIG, is a process in which an arc is struck between a consumable metal electrode and a metal workpiece, or the base metal that you're going to weld on. Flux core arc welding, or flux, is similar to MIG except for the electrode wire that is used. MIG is a solid wire electrode, and flux core uses a tubular wire electrode that contains flux and alloying materials. Basically, this MIG wire is the copper wire most commonly seen, and the flux core is a darker wire that's tubular, that's a softer metal. It's the exact opposite of a stick rod, where the stick rod, the flux is on the outside and the metal wire is on the inside. For flux, the metal sleeve is on the outside and it's filled with flux, hence the name flux core. A MIG and flux welding station, gas metal arc welding, or MIG, and flux both use continuously fed wires. The wire is the electrode. The flux process is used to weld only ferrous metals and nickel-based alloys. Flux is generally performed semi-automatically. That means us with a gun, pulling the trigger, starting and stopping, and can also be used with fully automated machines with excellent results. The fully automated machines would be the experience I had with it would have been sub-arc welding. It's a big machine. You just kind of set it up and it can weld for as long as it can go. As long as you dial up the parameters, you set it, it kind of runs itself. Kind of all you do is chip slag behind it. Flux core single shield or self-shield flux core. You can hear it. It's called inner shield. It's called. The process shields the weld with gases formed when the flux agents within the hollow electrode vaporize in the heat of the arc. Same premise again as stick welding. We take a look at this figure. We have our weld bead following us, cooling down as we go. This is the wire here. You can see the center is the flux cord center. The outside would be the actual metal itself. This is your contact tip, and this is your puddle. The big thing with this is in the figure you don't see a gas nozzle, which you'll see for regular flux dual shield. If you take a look in your book, here's a bigger picture in the book. If we start out, we have our contact tip from our machine, the tubular wire that's coming out, flux core wire. You can see in the center, this is our flux-coated powders, deoxidizers, and fluxing agents. We have our arc struck in between our base metal and our wire. That's creating our puddle, or our weld pool. Obviously, following behind us then would be our weld bead. The big thing about this figure is that it doesn't have a gas nozzle. The self-shield flux or the inner shield flux, because there's not a gas shielding it too, it's just the flux inside the wire. you don't need the extra protection of a gas nozzle. If we go to the second figure, obviously this would be the dual shield, FCAW-G, G for gas dual shield. So you have two shielding agents. You have the flux inside the wire and also the shielding gas, similar to what you would have for regular MIG welding. If we look, gas nozzle, you can see our shielding gas surrounding our weld pool to cool it and protect it from the environment. We have our arc transfer, the weld puddle or pool, our weld bead, and then our slag, just like you have with stick welding, covering our weld. Flux core self shield and flux core gas shield. The advantages and disadvantages. The self shield, you can use it outdoors because of crosswinds. You don't have to worry about losing your shielding gas. It does well in and out of position welding, which would mean anything outside of flat or horizontal. So welding vertical and overhead, it's a little easier than the dual shield. High weld spatter and high levels of smoke. Slag is harder to remove and lower deposition rate. So you're not putting out as much. The wire is not as thick as you can use with the dual shield, so that also makes it a little easier to weld out of position and harder, or have a lower deposition rate. Use more indoors because you can't have the winds to blow away your shielding gas. Shielding gas keeps oxygen and nitrogen away from the weld, so the welds are a little bit nicer with the dual shield. Produces a weld with good mechanical properties, produces less spatter and high deposition rate. You can use with the dual shield a thicker wire so you can put down more weld bead. Gas metal arc welding or MIG welding station, constant voltage, direct current, our arc welding power source, electrode wire feed mechanism, shielding gas cylinders and flow meter, gas regulator. MIG welding gun includes shielding gas hose and coolant hoses. We'll just have the shielding gas hose, no coolant hoses. Workpiece lead, which would be called our ground, electrode wire, and optional coolant systems, which we don't have, remote controls, which we don't have. We do have a booth table and ventilation system. Here's a diagram of a MIG welding outfit. If we start with our cylinder, we have our shielding gas, which we use for MIG is 75-25, 75% argon, 25% CO2. I think Airgas calls it Stargon, VS maybe. Off of the cylinder valve, we have our flow meter, our regulator actually, and then our flow meter is on our regulator. Our regulator is going to tell us how much pressure is left in our cylinder. Our flow meter is going to regulate the flow of gas out the end of our gun. It's cubic feet per minute, so we're going to want to set that to make sure that we got enough coverage over our weld. That hose connects into our wire feed control. For our Miller XMTs, our wire feeder is external. For our Lincoln 350 Power MIGs, the wire feeder is internal. Off the wire feed drive motor, we'll have, or off the wire feeder, we will feed into our wire feed drive motor. Those are the little wheels that the wire runs through, clamps it down, and pushes it or pulls it, the wire through our lead with to our gun. In this setup here, this looks more like that sub-arc welding kind of setup that you see where the wire wheel is above and then it feeds down through your base metal. Most of your wire feeders, the roll is going to be connected to it. Off of our feeder, then we have, like I said, our lead for our gun, our cable with an insulator in it that the wire runs through. Down, what we're welding on is called our workpiece, or our base metals, and then this blue line here would be our ground clamp, which is connected to our power source. If we take a look at figure 7.3, it's a schematic drawing of a MIG outfit. A complete station would include the arc welding booth and ventilation system and a workbench. The diagram is a combination of both semi-automatic and automatic gas arc welding outfit. The auto torch is used for automatic welding. It is replaced with a handheld gun for semi-automatic welding. So like I talked about, the sub-arc welding, where you kind of set this up and it runs on a wheel up and down to make welds. You kind of just clean up after it. And then we would replace this out for what the welding we're going to be doing, which is a semi-automatic, where we're hitting the trigger, the wire is coming out for us, but we're actually manipulating the puddle, carrying the puddle, shutting the gun off. If we start here with the cylinder, is our shielding gas. Off our cylinder valve, we hook up our regulator. Just like an oxy fuel, our regulator only has one gauge though. That gauge will tell you the cylinder pressure inside. Off of our regulator is a flow meter. A flow meter is what's going to tell us the rate of gas that's going to come out of our cylinder at the end of our gun. With the hose from the flow meter, it connects into our wire feeder control. Our wire feeder control is going to have our drive rolls in it. It's going to push or pull our wire through from our wire wheel or reel through the drive rolls to our lead for our gun, and then out the end of our gun. It has power coming from our power supply and the gas coming from our cylinder. In our gun lead, we have an insulator that makes sure that the flow or the pushing or pulling of our wire gets completed and comes out the end of our gun. Our gun will have a trigger, contact tip, nozzle, all that fun stuff. A flux core welding station, MIG and flux core dual shield welding stations use the same equipment. Single shield arc welding uses a different welding gun that does not use welding shield gas equipment. A gun for single shield may be air cooled or water cooled. So let's take a look in your book. Here is a look up top here at a example of a single shield flux core gun. Obviously here we don't have a gas nozzle on the end. Our contact tip is exposed because we don't need to shield it from the gas. It also usually has this metal protector for your hand. A lot of times the single shield gets, you're using pretty high temperatures, your voltage is set pretty high. So this is just a cover here to kind of protect your hand from the heat. Down here at the bottom is a typical welding gun for the dual shield. Looks exactly like the same gun you'll use for MIG welding. It has the gas nozzle to kind of cover the gas, keep it close to our weld so it doesn't leak out the sides, and our contact tip is recessed into that gas nozzle. MIG and flux core power sources. A MIG and flux use a constant voltage welding power source. Power sources include transformer rectifier, inverter, and engine-driven generators. If we take a look in our book, here's an example of an inverter power source. We have our little box welder. It looks like a Power MIG 180 Lincoln. If we start going around, we have our ground clamp, our gun itself with the nozzle and the contact tip sticking out. We will be welding flux core. We have our drive rolls here, our contact tips here. Here's another nozzle that we would use for MIG wire. Here's our regulator. Here is a CD on how to use it. The wire types here, the gold type or copper looking type would be regular solid wire. The gray looking or darker looking colored would be your flux core. This would be your box here with this compartment would open up, and this is what would hold your rolls of wire. Your drive wheel and everything would be internal, obviously, in this welder. We come down, we have a engine-driven welding type of welding machine. This is something you would have either on a trailer or on the back of your truck. It's going to be engine driven, so you're going to have some kind of fuel. Doesn't have electricity. It would have constant voltage terminal and constant current terminal. Your workpiece lead would be your ground. Direct current electrode positive is used. MIG and flux power sources. Direct current electrode positive is used for MIG. Direct current for flux can be either direct current electrode positive or direct current electrode negative. I've never used direct current electrode negative for flux. If you remember the difference between the beads for direct current electrode positive, it is a deep penetrating bead with a narrow width, and for a direct current electrode negative bead, it is a shallow bead with a wider width. The only time that I've ever used direct current electrode negative is on really thin types of metal, like sheet metal almost. Most times when you're dealing with anything over, I would say, 1/4 inch, you're going to be using direct current electrode positive. The constant voltage power source maintains a constant arc length. The arc welding machine amperage is changed proportionately when the wire feed speed is changed. So anytime we're dealing with dialing in our machines and it talks about wire feed speed, you can almost correlate that to amperage like you did for stick welding. Volt amperage curve, the output of a constant voltage power source has a very flat volt amperage curve. Slope is the change in current due to a change in voltage. Some welding machines allow the slope to be changed. So basically, we want to make sure that when we're welding, we keep our arc length the same or constant throughout our weld pass or our weld bead. This way that if we start to long arc, we start to draw our arc away from our welding source, our amperage is going to raise to keep that arc constant. So we want to make sure, like I said, we just keep our arc length consistent the whole way through our pass. Wire feeders for MIG and flux. Wire electrode used in MIG comes in large coils or drums that contain hundreds of thousands of feet or wire. We're not going to deal with anything like that. Our wire will come in 44-pound rolls. Wire feeders may be contained inside the MIG machine or separate from the machine. I talked about that earlier. The Millers, it's external. The Lincolns, it's internal. Wire feeders consist of a coil-mounted device, a set of drive wheels for the wire, and an adjustable constant speed motor. Wire feeders for MIG and flux drive rolls have one of 3 groove designs: a V groove, which is used for MIG solid wire, a knurled groove, which is used for flux core, and a U groove, which is usually used for aluminum, which is more of like a flux core type wire. Drive rolls are designed to work with a specific electrode diameter. Let's take a look in your book. So here's a better look at our drive rolls. If we look at this set here, it looks like a V groove set used for MIG solid wire. It has 045 on the top side. So this track here would be for 045 diameter wire. This track here would be 035. Similar with these, this looks like a knurled set. Let's see if I can draw it here. If we look at those kind of teeth there, because flux wire is softer than solid wire, you need those to kind of clamp down and pull the wire through, your lead and throughout the machine. The U set of drive rolls are usually, they're 2 pair. Because aluminum is so soft, you'll need a set of drive rolls at your power supply and then, or your drive reel, and then all the way at your gun too. Here's a look at a 4-roll wire feeder. If this is our wire feeder, we just lifted this hatch up like you see here on this machine. These are our drive rolls in action. This is our tension adjusting knobs. We would flip this down, this would flip up, flip this down, this would flip up. Our wire would come in through this inlet, come all the way through in those grooves like we saw on the drive rolls, and then come out. Our gun hookup would be on this inlet. Let's see if our book has a better look. If we take a look here, our wire that we start out with, our roll of wire would be hooked on here, our spool knob or hub. It would come down, it would feed underneath and come in through our drive rolls and then out this end. Big thing to look at here is this hatch that covers our drive rolls and our wire. If you flip that up, it's going to tell you specifics on what to set the machine at, like our voltage, our wire feed speed to correspond with the diameter or the thickness of our metal. It'll also tell us, if you kind of can look here at the tensioner controls knobs, there's numbers for the different wire. You're going to have a different number to tension those drive rolls to clamp down on your wire to be able to pull it through the machine. Inch switch and purge switch. An inch switch or jog switch on the wire drive control panel is used to rotate the drive motor slowly. So on our Miller XMTs, there's an inch switch and a purge switch. A purge switch is on the wire feeder or power supply, may be provided to clear the hose and gun of air. It's also used to set your gas pressure. It's another way you can do that without actually pushing the trigger or pulling the trigger to have the wire come out. You can kind of hit that switch and set your flow meter. MIG and flux shielding gases. Shielding gases used for MIG can be inert, reactive, or a mixture of both. Inert gas is heavier than oxygen. The two main inert gases are argon and helium. So, like I told you earlier, our two gases that we use for MIG are 75% argon, 25% carbon dioxide. Inert gases do not react with other chemical elements. Argon and helium are used in MIG. Reactive gases react with other chemical elements. Carbon dioxide and oxygen are used for MIG. Gas mixtures or 100% carbon dioxide are used for weld steels. I've heard that, for flux, I've never used 100% carbon dioxide, but I've heard for flux, you can use it. It runs a lot better, but it's just fumes are really, really bad for you. It's very cloudy. It's kind of tough to work with. So we normally use for our flux core 75-25 argon to carbon dioxide. Pure argon is used to weld most non-ferrous metals. So if you're going to weld aluminum, it's going to be straight argon. Hydrogen and nitrogen are used in specialized applications. And the gas and gas mixture selected is determined by the metal and the arc transfer method desired. That's a key. When we do MIG pulse, we're going to use trimix, which is going to have argon, carbon dioxide, and helium in it. Argon, inert gases, argon and helium, they're heavier than oxygen. So when that gas comes down, it's going to push your oxygen and nitrogen that are in the atmosphere away from our weld, so it's actually shielding it, protecting it from those atmospheric gases. So there you go. That's the shielding gas. It is actually shielding. It's heavier than oxygen, and it's pushing everything away. If you remember from the safety chapter in your book, chapter 1, it tells you about not welding in a confined space with argon. It's because it'd be dangerous. You have to have some kind of draft in there because the same thing. You're welding constantly, that argon is pushing oxygen out of that room that you're in. So you just want to be careful if you're ever welding in a confined space with flux. Shielding gas cylinders. The cylinders are available in various sizes. Cylinders are manufactured to Interstate Commerce Commission specifications. Some gases are stored as liquids. Oxygen usually. The quantity of gas in a cylinder is determined by the high pressure gauge or volume scale if stored as a gas, the weight if stored as a liquid. Safety slide, threading cap securely over the cylinder valve whenever cylinders are moved or in storage. A cylinder truck is recommended for moving cylinders. Fasten cylinders to a wall or stable object when in use. Always store and use gas cylinders in an upright position. Use and store cylinders according to the local building and fire codes. Once we get into the shop, I'll take you on a little 10-cent tour where we keep our cylinders full and empty. If you're welding with flux core, you're going to be on the manifold system. If you're welding with solid wire, whether it's short circuit or MIG pulse, you're going to have to change your own cylinders. We always want to use a cylinder cart. The cylinder should always be in an upright position. The cylinder always should have a secured cap on it, and it should always be chained up. When we take it through the shop, you're going to want to go through the roll-up door. The cart won't fit through the regular doors, so we always want to make sure that we're heading out the back end of the shop through the roll-up door. And like I said, we'll chain our cylinders, our empties, close to the end roll-up door where air gas can come in and easily pick them up and service them. And then the other one, the full ones, are behind two gates. So anytime that you run out of gas, come get me. I'll give you a hand, make sure that we have everything hooked up right. Shielding gas regulators. Regulators control the rate at which gas is expelled from the cylinder. Flow meter scales are accurate only if gas entering them is about 50 psi. So let's take a look in your book. Here's a better look at a regulator and flow meter. If you look at our fitting, this should be 1 1/8 fitting that'll hook onto our cylinder valve. We have our regulator with our cylinder pressure gauge right here, and then our flow meter to the left. If you take a look, there's a little silver ball right there. Let's see if I can look at that right there. That is going to tell us our PSI for our flow meter. If we open this up, it's going to take our pressure out. If we tighten it in, it looks, no, by this drawing on the outside here, if we go counterclockwise, it's going to increase our PSI. If we go clockwise, it's going to let it out. But the main thing you want to know is this silver ball, the top of the silver ball, not the center of it, that's going to tell you your reading. So if I get the top of the silver ball to the 40 mark, then I'm at 40% or 40 PSI. If I take the center of that ball to this line, I'm at 45 PSI. So that's a big thing to remember. And another thing, it's kind of a pet peeve of mine, is when you get done at the end of the night or end of the class, let the gas out. That way the next person, when they open the cylinder valve, that this ball doesn't go ping into the top of the flow meter. I doubt it's going to crack the top of the flow meter, but it's just better off not having that thing snap all the time. We want to kind of keep them as best as we can and take care of the equipment that we have. So it's just a pet peeve. I mean, if you forget, it's no big deal, but I would like to try to just relieve that gas after every class. More about flow meters. They measure the rate of gas flow. The volume of gas coming out of the nozzle is measured, and a different flow meter for different scale must be used for each gas. So let's see what we have in your book. So here is the picture again. It's a little bit bigger, and hopefully you guys can see this, but when we get into the shop, you're going to notice it on our flow meters. We have different ones for, for flux and for MIG. You want to be careful because there's going to be writing on the sides here. I don't know if you can see it very well, but it'll say argon plus CO2 or just straight argon or helium. You want to make sure when you're setting this ball and you're setting your pressure for your gun that you're looking at the right reading, because there's going to be a couple different readings on there. So just take a look at your cylinder, make sure you know what gas you're using, and then when you try to set your flow meter, make sure you're on the same number system as for your gas. Gas mixtures for MIG to overcome the tendency for filler metal not to flow to the edges of the weld. A gas mix is used. For steels, oxygen or carbon dioxide is added to argon. We'll be using carbon dioxide, not oxygen. Adding oxygen or carbon dioxide to argon or helium causes the shielding gas to become slightly oxidized. This can cause porosity in some ferrous metals. Like I said, we're not going to use oxygen. We're going to use carbon dioxide. If you start to get porosity, it's not really coming from the gas. I would say it's coming from a lack of gas. Your arc length is starting to get probably a little long, or your arc is too close. Your nozzle's too close to the weld, so the gas is hitting your base metal and flowing onto the outsides, or your arc is getting too long and your gas is coming out of your nozzle and it's not getting to your weld. Argon and helium gases for MIG. Argon and helium are generally used with non-ferrous metals. What is non-ferrous? It doesn't have iron in it. So aluminum is the big one there, copper. Helium is used when high heat input is required in a welding application. So like I told you earlier, MIG pulse we're going to use a trimix with helium in it. Because MIG pulse, you're going to be using higher voltage and wire feed speed than you would for the regular short circuit MIG. Argon is heavier than helium and provides a better shield. Argon is often used for out-of-position welding because of its lower heat conductivity, and argon costs less than helium. Here's a look at MIG shielding gases and penetrations. The weld bead contour and penetration are often affected by the gas used. So let's look at the book. You get a better view. This figure shows the shape and depth of penetration of beads obtained with various shielding gases used for MIG. If we look at argon, it's got that wider width and a narrow penetration. If you look at argon and CO2, which we'll be using, it's also got that wide coverage, but a deep penetration with a wider bead. So it's good for all around welding. If you see here just straight out argon, you got undercut on the toes of your weld. That's no good for when you're welding, obviously, carbon steel and such. So it's better for non-ferrous metals. Helium, I guess, would be used more for thinner metals because you're not getting that deep penetration and you're getting wide coverage. A mix of argon and helium, you're still getting wider coverage but not as deep penetration. And then carbon dioxide, straight carbon dioxide. Like I said, I've never used it. I've talked to the guy from Airgas because I did a lot of flux core welding at my last job. And he said CO2 is the best for carbon steel on heavier, thicker stuff. So we're talking like 1-inch plate or something, you want to use carbon dioxide. The pain of it is, though, you get all this spatter, so it's going to take you a little bit longer to clean up after you're done welding. And the fumes. He said the fumes are very toxic. It's cloudy. You got to have a lot of ventilation to use carbon dioxide. Shielding gases for flux. Flux single shield does not use any external supplied gases, so you don't have to worry about it. A lot of times, if you're going to buy a welder for your home to have in your garage or something, you get the single shield. That way you don't have to worry about changing out bottles or setting up an account with Airgas. The most common shielding gas is flux dual shield. With flux dual shield is carbon dioxide. Gas mixtures are also used. We're going to be using 75% argon, 25% carbon dioxide. The proper combination of shielding gas and the electrode is required. So always kind of check that out too, because make sure you have the right combination wire with the gas you're using. MIG welding gun. The welding gun directs the welding electrode to the weld. The gas hose, electrode lead, and liner are all built into one large cable. MIG welding guns are usually air-cooled. Water-cooled guns are required for continuous welding or welding at amperages above 300 amps with argon shielding gas. Spool guns have self-contained wire drive units. So when I talked about welding with aluminum before, where you have the drive rolls at your wire feeder, and then you also have drive rolls at your gun, because it's so soft, you need that extra set of pair to pull it through your whole system. A spool gun is similar in that fact. It's usually, spool guns are only used for welding aluminum. A pull type gun has a motor and drive rolls in it, which pull the electrode. That's the same principle. And a push-pull system, the welding gun pulls the wire while the wire drive at the power source pushes the wire. MIG welding guns for automatic MIG, straight neck and nozzle, no handle or trigger, attached to a carriage or other mechanism for welding. That automatic welding, like I was talking about sub-arc welding, you kind of just dial up the machine, you kind of start it off, and it goes on its own. Welding guns for robotics have a bent neck or attached to a robot. We don't have to really worry about that in this course. Flux welding gun, the electrode selected determines the type of welding gun required. The dual shield requires a different gun than the self shield. We went over both of those. The dual shield will have a nozzle to protect the gas to shield our welds. For the self shield, the contact tip will be exposed. There will be no nozzle. You don't have to worry about it because you don't have that gas. Guns can be water cooled or air cooled. Contact tips. The contact tip transfers electrical current from the welding gun to the electrode wire. A contact tip tube threads into a contact tube adapter or diffuser, and the adapter threads into the welding gun. Let's take a look in your book. All right, as you can tell, there's different styles for each different gun. If we look here, we have our nozzles on the very end, our contact tip, which screws into, or in case of the Miller XMTs, it'll just sit in to our adapter or diffuser. I like to call them a diffuser. I don't really call them an adapter, because if you look at those little holes there, it's going to diffuse our gas, and then we have an insulator. So if we look here at our gun, the neck of our gun, we have our insulator on first that kind of covers the neck from this piece right here. Our diffuser screws onto there, our contact tip into our diffuser, and then our nozzle on top of that. This setup here is what I was talking about with the Miller XMTs. This contact tip just sets inside this diffuser, then the nozzle comes up on top. I sort of like this setup because if your wire melts to your contact tip and you got to change it out, you can just kind of hit the trigger and that contact tip will fly out of there because it's not screwed in. If you're using the Lincoln 350 Power MIGs, and it's more similar to this style, and this is screwed into your adapter and you've got your wire melted there, you're going to have to take that contact tip off while threading it melted to the end. It's kind of a pain in the butt. But unfortunately, once the contact tips get a little worn, they are consumable, so they won't last forever. Once they get a little worn, then sometimes, or if you don't have your welder set up correctly, you'll get burned back and it'll melt to your contact tip. It'll have to be changed. When that wire comes out of the contact tip hole, it's rubbing across the side of the hole to keep the electrode, or to keep the electricity, the electric circuit connected. So once it wears that hole almost diagonal, it'll wear, so it'll get sloppy, basically, is what I'm trying to say. So just keep an eye on that. You want to make sure you keep your contact tips changed. Like I said, it's no big deal. If it's worn out, just come get me. We'll get it changed out. A nozzle fits on the end of the gun and directs the shielded gas to the weld area. Nozzle designs vary. Exit diameters are measured in 16th increments. If we take a look in your book, there's different liners. A liner is installed in the cable that carries the electrode from the wire feeder to the welding gun. For most applications, a coiled steel wire liner is used. A nylon liner is used for aluminum electrode wire. If we look in your book, it'll show you a picture. This is what your liner looks like. It has the end that comes out of your gun, and then this hooks up to the end of your that connects to the power supply itself. This is what the the liner looks like as it comes out of the neck of your gun. Liners should last quite a while. I've had to replace one or two throughout my entire welding career, so hopefully we don't have to worry too much about changing a liner. The only time is when you're trying to pull wire through. Don't really yank on it, because then that could affect your liner. Other than that, we really shouldn't have any problems with replacing liners. Welding pliers or welpers are useful tools, function as a wire cutter and needle nose pliers. There's actually a couple different things you can do with these. The needle nose will help you kind of pull the wire through. I'll show you on your book, but many arc welding machines have a remote control circuit switch and external plug, remote adjusters. We don't have to worry about any of these. We don't have them. But the welpers, if we look in our book, here's a better picture of our welpers. If we look here, you can kind of see the threads so that we can clamp onto our wire and pull it if we need to. We can also kind of stick these down into our nozzle to kind of clean it out. If you look at this round hole right here, that's going to help us tighten and loosen our contact tip, our shears for the cutting the wire, and then down here, this will clamp onto your nozzle and help tighten it or loosen it. Once you're welding for any period of time, all this stuff is going to get extremely hot, so we don't want to be using our hands. So use your welpers to kind of take stuff on and tighten stuff back up. MIG and flux core electrode wire. MIG continuous solid electrode wire is sold in spools or drums. Ours is going to be on spools, the 44 pounders. Typical flux electrode wire is larger in diameter than MIG electrode wire. Like I told you, all of our MIG solid wire is going to be 035. All of our flux is going to be 045. Electrode wire selection is based on base metal composition, base metal properties, cleanliness of base metal, shielding gas, and welding position. This cleanliness of metal, flux core, it's a little bit more forgiving on dirtier metals, rustier metals, paint and stuff like that. Solid wire is more for fresh steel, clean steel. You always want to clean your steel before you start working on it. But like I said, flux is a little bit more forgiving than the solid wire. MIG electrode wire. MIG electrode wire is usually continuous solid electrode wire. Metal cored wire is the second type. AWS has an identification system for MIG electrode wires. If you look here for aluminum, the big numbers are 4043 and 5356. If you've had TIG, you'll notice that's the same stuff, the same numbers you use for your filler wire. For carbon steel, ER70S. If you had oxyfuel, weld 102, then you've heard that ER70S. That's the filler rod we use for oxyfuel welding. That means, yes, if you took wire from your MIG gun and went over and tried to oxyfuel weld, it would be the same. You can use it the same way. If we go back and learn what each of these mean, the designation, the electrode designations, E for electrode, R for rod, 70 is your tensile strength, so 70,000 pounds per square inch. S for solid, -6 would be your chemical composition, the oxidizers and the denitrizers, or whatever is in that filler rod too. Deoxidizers and denitrifiers are elements added to most electrode wires to reduce porosity in the finished weld. They remove oxygen and nitrogen from the weld. Magnesium and silicone are also examples of deoxidizers. Magnesium and silicone, when you're using MIG, you'll see it on the finish of your weld. It'll kind of look flaky, almost like slag, but not slag. That is the silicone residue. MIG electrodes for stainless and aluminum, we're not going to do that one. Flux electrode wire. Flux welding electrode wire is continuous wire found onto spools. The U-shaped area of the wire is filled with granular flux and alloying elements. A wide range of flux core wire is available in different core elements. The function of flux, added deoxidizers and denitrifiers, add alloying elements, form gases to shield the weld area, create a slag covering over the weld bead. So that's the big difference you're going to have with MIG and flux. Just like in stick welding, you have the flux on your welding rod, you have flux in the flux core wire, so you're going to have slag. You're going to have to clean that out every time. Make sure it's clean. We can't burn flux out, so if you have slag inclusion, you're going to have holes, Swiss cheese looking things in your weld. So anytime you're welding, after you get done, chip and hammer or wire brush, I would recommend a wire wheel for as much as we're going to be doing it, to make sure that weld is clean, all that slag is taken off. Other functions of flux: stabilize the arc and trap impurities in the molten metal and float them onto the top of the weld to form slag. Flux electrodes for carbon steel, E70T1 is what we use, and with the designations for that electrode, E electrode, 7 is 70,000 pounds of tensile strength. 1 is the all positions for welding. It's only either going to be a 7-0 or a 7-1. 0 is for flat and horizontal position. 1 is for all positions. The T is for tubular. And the -1, again, would be your chemical compositions that are inside the flux. If there's another number after the dash, the second number would be the gas shielding that you should use with that wire. Flux electrodes for carbon steel. Dash numbers indicate the following: electrode polarity, whether you should be using direct current electrode positive or negative, if a shielding gas is required, and the number of weld passes recommended. The shielding gas is to be used and can be indicated by the letter in the final position. Low alloy, we're not going to worry about that. Getting here towards the end, smoke extracting systems, MIG and flux produces we're getting towards the end here. Smoke extracting systems, MIG and flux processes can produce smoke. Gases produced can be toxic. Different methods are used to remove smoke and toxic gases. A gun equipped with a fume extractor, I wish we had those. We don't. A large fume extractor system, that's what we do have. We want to make sure that system is close to our welds and our weld area, that it's taking the fumes out, we're not breathing that stuff in, but we don't want it too close because obviously it would take our shielding gas. So if we start getting porosity, one thing, arc length would be, we might be getting too far away from or too close to our weld, but it also could be that our fume collector is too close and it's actually pulling the gas away from our weld. If welding is done in a closed area or hazardous metals, it may be necessary to wear an air-supplied breathing apparatus. With the COVID-19, we're going to be wearing masks in there anyway, so hopefully we're not breathing in all these fumes. A smoke extractor and filter are set up at the top of the MIG power source. A pickup hose is attached to the MIG gun. In this picture, obviously, like I said, I wish we had that stuff. Unfortunately, we don't. Safety slide: when using an air supply respirator, make sure the system is operating properly before entering a closed area or doing welding. Because an air purified respirator does not remove toxic fumes, it should not be used for protection in a closed or contaminated area. Filter lenses for MIG. Because of the cleaner atmosphere of the arc, the operator must use a welding lens with a darker shade. I would crank it all the way up, whatever your hood has. It would be a shade 12 or 13, and then if it's too dark, you can kind of work your way down. Don't start out at like a 10, blind yourself, and then work your way up, kind of work your way down. This will reduce eye fatigue and prevent possible eye damage. Most helmets or gas arc welding use a clear cover lens and a filter plate to keep lenses clean. Flux core, they're going to get melted. I mean, they're going to have a lot of sparks. If we're welding overhead, it's going to get, that lens is going to get damaged. So unfortunately, you're going to have to invest in some lenses. They're pretty cheap, but the more you replace them, the better off you're going to be able to see, the easier it's going to be to weld, and your welds are going to show. You're going to be able to make nicer welds. So yeah, it's investing in a little bit of money to make it a lot easier on yourself and make better welds is a good investment. Protective clothing. Leather clothing provides the best protection. Heavy wool or cotton can be used or worn. Dark clothing reduces the reflection of light behind the helmet, and leather gloves should be worn. The leather gloves thing, when you're flux core welding, it gets hot. You're going to be running, even when you do MIG pulse, the voltage and the wire feed speeds are going to be higher than they would be for the short circuit. So a lot of students, they get a protective cover for their offhand because we like to get close to what we're welding, and that heat for those processes is going to be very, very hot. And I would recommend run a pass, give it a minute or two, run another pass. Don't just constantly run, because eventually that base metal, I've seen students that have it like glowing orange and wonder why they're getting burnt even through with having a glove on. You gotta let this stuff cool down, especially, like I said, for flux and MIG pulse. But there are heat shield or reflective heat resistance cover that you can put on for your gloves. I recommend that when we get into the flux. Our final slide, it's been a long journey. Safety review, make sure electrical connections leads are in good condition. We don't want any copper showing. Make sure when you're welding too that your leads are completely straight. You don't want them coiled. Any kind of kink or something like that could affect the wire getting through your lead. Use adequate ventilation and filters to protect against fumes. Wear proper clothing to prevent burns. I would say layers. Use layers. That way, if it burns through the first layer, you have another protective layer underneath. I know it's going to be hot in there in the shop, especially with all them welders going on, but protect yourself at all times. If you don't want to get burnt, protect yourself. I would say any bare skin, like I like to wear a V-neck, any kind of bare skin with the infrared rays that are coming off this, there's a chance that exposed skin, you can get burnt. So you want to cover up, button up. It's not a fashion show in there. You want to protect yourself at all costs. Do not carry flammable materials in your pockets. No, any of the cigarette smokers, you don't want to keep your cigarette lighter in your pocket. Close pockets and roll down your cuffs on your pants. You don't want to get any hot molten metal stuck and then burn through your jeans or anything. Wear a welding helmet with proper lenses. I would recommend a welder's cap too. Always start with your settings on your helmet high and then work your way down, and place shielding curtains around the job. Well, we did it. We made it through. I know it was a longer video than I even expected, but there's a lot of information there. Hopefully we kind of sewed up any loose ends and you got something out of this video. I want to thank you again for clicking on the video PowerPoints for this chapter, and we'll see you in the lab.